Hey there, in this video we're going to tackle the first derivative test and how it applies to the graph of a function. And we're going to make the connection or emphasize the difference between finding the absolute extrema of a function on a closed interval versus finding the relative extrema. So let's look at this example. Let f of x be this function. In two parts, we want to find the absolute extrema on the closed interval. So at first glance, I see I have a square root, and I see that my interval contains negatives, so I'm a little bit worried about the domain of the function. So let's find the domain of our function real quick. So find the domain of f of x to make sure that we can find absolute extrema on that closed interval. So what do you know about the domain? So square roots, we can't take the square root of a negative number, so we want the inside of the square root to be greater than or equal to 0, right? The square root of 0 is 0, so we can take the square root of that, and then we want anything in here to be positive. So that means that x has to be greater than or equal to negative 5. So the domain of f then is from negative 5 included all the way to infinity. So the interval negative 4, 1 is definitely in the domain. So we are okay in terms of the domain. Now we have find the absolute extrema on the closed interval. So we have to make sure that the function is continuous on that closed interval so we can use the extreme value theorem. Remember from the previous sections we talked about the extreme value theorem tells us that if a function is continuous on the closed interval, then the function attains its absolute maximum and absolute minimum on that interval, and they either occurred at the endpoints or on the critical numbers that lay inside that interval. So is it continuous? So f of x, this is a polynomial times this radical, both of those are continuous. This product ends up being continuous, so we can say definitely f of x is continuous on the closed interval negative 4, 1. Therefore absolute extrema exist. And so now we find them. And as we said, the extreme value theorem tells us that they occur at either the endpoints or at critical numbers. So we need to find critical numbers first, just to see are there any critical numbers that fall in our interval negative 4, 1. So what are critical numbers? Critical numbers are where the derivative is 0 or undefined. So let's go ahead and find the derivative of our function. So here is our function. So let me rewrite it. Let's rewrite it so that we can take the derivative. So this is x squared times x plus 5 to the 1/2. And so because I have the times there, that means that I need to use the product rule when I take the derivative. So f prime is, so product rule says the derivative of the first, so 2x times the second left alone plus the first left alone times the derivative of the second. So that we'll use the general power rule. So 1/2 x plus 5 to the negative 1/2, and then by chain rule times the derivative of the inside, but that one is just 1. Lucky for us, we don't have too much of a difficult chain rule there. So let's simplify it because we want to be able to solve for x. So I'm going to rewrite this back with in its radical form. And this is a negative exponent, so that's going to go on the bottom. So I'm going to have x squared in the numerator divided by 2. And then that's going to come down as a positive 1/2, so square root of x plus 5. And now we need to find critical numbers, so set that equal to 0. And one thing we can do is get a common denominator. So there's a number of things you can do, right? You can subtract this to the other side and then cross multiply and try to solve for x that way. I'm just gonna do a common denominator. So my common denominator is 2 times the square root of x plus 5. So that means I need a 2 square root of x plus 5 here and 2 square root of x plus 5 here. So this is going to be helpful because those will cancel. the square roots. So I'm going to have f prime of x is 2 times 2x, so it will be 4x times x plus 5, right? Square root of x plus 5 times the square root of x plus 5. The square roots cancel, plus x squared, and now they will have the same denominator. And let's distribute that 4x in. So I'm going to have 4x squared plus 20x plus x squared over 2 square root of x plus 5 equals 0. I guess I could have set it equal to 0 way after I simplified. So 5x squared plus 20x over 2 square root of x plus 5 equals 0. Now a critical number is when the derivative is 0 or undefined, and a fraction is 0 when the numerator is 0. So f prime of x is 0 when 5x squared plus 20x is 0. So let's take out a 5x, and I'm left with x plus 4 equals 0. So either x is 0 or x equals -4. So -4 is a critical number, and it's also one of our endpoints. So that one is a double duty there. And the f prime of x, the derivative is undefined when, since we have a fraction here, when the denominator is 0. So when 2 square root of x plus 5 is 0, and that's going to give us x is -5. But this is not on our interval. So not in -4, 1. So we don't need that critical number. But essentially from here we get 3 critical numbers. It's just that one of them, the -5, is not part of the interval. Alright, so now that we have our critical points, we can test for the absolute extrema. So remember, absolute max is the largest function value, and absolute min is the smallest function value on the interval given. So the things that we're going to test then are critical numbers that fall inside the interval, so 0 and -4, and the endpoints, -4 and 1. So -4 is common, so we'll obviously just test it once, only include it once. So let's try that. So let's go to our table to plug in the values. So we'll have our x and f of x, which is x squared times the square root of x plus 5, right? When we're finding the y value, because we want to compare the y values. So I'm going to have -4, 0, and 1. So -4 is an endpoint. 0 is a critical number. And 1 is also an endpoint. -4 is also a critical number, but we're just going to go with it's an endpoint. So let's plug it in. So when you plug in -4 into the function, the y value is going to be what? So -4 squared times the square root of -4 plus 5. So we're going to get 16. And when you plug in 0, y is 0. And when you plug in 1, what is this? So this is going to be 1 squared, so that's 1 times 1 plus 5 square root, which is then just the square root of 6. So what is the largest one? So our absolute max is going to be 16. So this is the absolute maximum, is y equals 16, and it occurs at x equals -4. And what is the absolute min? Our absolute min will be 0. Is y equals 0, and it occurs at x equals 0. Okay, so that's how we find our absolute extrema, absolute max and absolute min. Now for part B is asking us to determine the intervals where the function is increasing and decreasing. In a prior video, I already kind of covered how to determine when things are increasing or decreasing, but I didn't really go into why that is. And now that we know about the mean value theorem, so if you look in our book, the reason that we have when the derivative is positive, the function increases, that is proven using the mean value theorem. The mean value theorem says that if a function is continuous on a closed interval and differentiable on an open interval, then there exists a point in that interval where the derivative is equal to the slope of the secant line connecting those points. And so as you go through, you start seeing that as a function, when the derivative is positive, the mean value theorem tells you then that those secant lines are increasing, and therefore we can derive the first derivative test. So our increasing decreasing test, which is also called the first derivative test, essentially says if the derivative is positive on an interval, then f is increasing on that interval. And if the derivative is negative on an interval, then f is decreasing on that interval. So back to our part B of this example, we want to determine the intervals where the function is increasing or decreasing. Now notice that here we don't have an interval, right? There's no interval given, like part A, where it asks us to find the absolute extrema on a closed interval. So determine where the intervals where the function is increasing or decreasing, that is assumed, since there's no interval given, that we want to find it on the entire real line. So we can say here on infinity to negative infinity to infinity. So then how do we approach that? Well, the increasing and decreasing test says if the derivative is positive on an interval, but we don't have any intervals, but we create them. So the first thing will be to find our critical numbers, which we already did in part A. When we found the derivative, we found the critical numbers to be, what were they? We had 0, -4, and we also had -5. That was where the f prime was undefined. So that's still a critical number. And we can probably see why it's undefined, because the domain of the function starts at -5. So where did we do the domain? The domain, right, is from -5 to infinity. So that is probably just like a dot. If I was going to guess what this function looks like, is at -5, it kind of, this is just following a standard square root function, but so it makes sense why the derivative is undefined there, because it's technically a corner, so it is not defined. This is not the actual graph, just an example of what it might look like, or why the derivative is undefined there. So those are critical numbers. And so using the first derivative test, I can split up my number line into those critical numbers. So I'm going to have -5, -4, and 0. And so we're going to test the first derivative. So f prime of x, I'm trying to see, is it positive or is it negative? And we're going to make a decision about what f is doing. Right? If the derivative is positive, then I know the function is going to be increasing. So let's see, and I usually like to write a little something above my critical numbers about what the derivative is doing there. So these are critical numbers because the derivative is 0, and this is a critical number because the derivative is undefined. And so now we pick test points in each interval, and we're going to test them into our derivative. So let me write over here what our derivative was. So once we factored out the 5x, this is our derivative, and so let's find test points. So what intervals are we going to test? So, oh, by the way, notice that because of our domain, do I need to pick a test point in here? Right, this portion of the graph is, these values of x are not in the domain. So I don't need to worry about that interval. If you forget to find the domain of a function and then you pick test points and things are coming undefined, or you're getting an error if you are using a calculator, it's likely because those values are not in the domain of the function. So it's really good practice to determine the domain of the function first and then continue to find your critical numbers. So we're going to test the intervals -5 to -4, and then -4 to 0, and then 0 to infinity. So here, let's pick x equals like -3, for example, and you plug it into the derivative. So what's f prime of -3? And again, we're not necessarily too concerned about the value, but more the sign. Is it positive or is it negative? So I'm going to have 5 times -3, -3 plus 4 over 2 times the square root of -3 plus 5. Again, I'm not too concerned about the value, but mainly the sign. So this a positive 5 times a negative, that's going to be a negative. -3 plus 4, that's positive, and the bottom is positive. So I have a negative times a positive, which is negative, divided by a positive, so that's negative. So the derivative in this interval is negative. What does that tell me about the function? The derivative is negative, then the function is decreasing. That's what the derivative test helps us with. Now in the interval -4 to 0, we can pick something else, say -1. So what about f prime of -1? So you're going to have 5 times -1, -1 plus 4 over 2 square root of -1 plus 5. And so we're going to have negative times a positive, so same thing, negative times a positive over positive. That's going to be negative again. So the derivative here is negative, which means that the function is decreasing. Be consistent with the colors here. And what about on the other side of 0? So for x equals in between 0 to infinity, pick like x equals 1, for example, then what is f prime of 1 going to be? So you're going to have 5 times positive 1, so that's going to be positive, and then positive 1 plus 4, so that's going to be positive, and the bottom is always positive. So now you're going to have positive there. So going back to our number line, the derivative is positive, so that means the function is increasing. And so now I have my intervals where the function is decreasing and where the function is increasing. So let's write it out. So we can say then f of x is increasing on the interval 0 to infinity, right? The one where I got the derivative is positive. And f of x is decreasing on, now here is decreasing from -5 to -4, and then -4 to 0. Notice that a -4 is neither increasing nor decreasing. So I can't say -5 to 0, ignoring the -4 there, because there the derivative is 0. We have a horizontal tangent line or something else going on there. So let's see. So f of x is decreasing on, we're going to say -5 to -4 and -4 to 0. At -4, the derivative is equal to 0, so it's neither increasing nor decreasing. What I imagine is happening there is you probably have what is called a saddle, kind of like with the cube root of x, right? This is, the derivative is 0 here, but it's neither a max nor a min, so that's not a relative max or a relative min. And so from here we can see also that you have decreasing and decreasing, so there's nothing going on there, not a max nor a min, so this is what we call a saddle. And then here you go from decreasing to increasing, so this is going to be a local min. If you wanted to find the value of the local min, then you will plug in 0 into the original function to find the y value, and we already did in the part A, so we have a local min y equals 0, and it occurs at x equals 0. And we have a saddle at -4. So it'll be interesting to look at the graph of this function because it starts at -5 and then it decreases and it does something funky, probably like a saddle, kind of like the x cube that is called a saddle, right? It doesn't change from increasing to decreasing or the other way around. So then we call it a saddle, and then you have a local min at 0. So these problems can take a long time. As you notice, this is already a 20-minute video, although I do talk a lot. All right, so in the next video, I'm going to record the rest of the examples that are in your notes.